Good morning, everyone. Today we are going to discuss one of the most crucial engineering decisions in electric vehicle development: how to select the right powertrain components. When we talk about the EV powertrain, we're referring to all systems that convert electrical energy into mechanical motion. This includes the battery, inverter, motor, reduction gearbox, driveline, and the controllers. Different applications, from a compact city car to an electric bus, require completely different choices. The reason is simple: powertrain components must be sized and selected based on performance targets, cost, range, efficiency, thermal limits, and vehicle weight. In this lecture, we will walk through each major component and understand how engineers make these selections. Every powertrain design starts not with components, but with vehicle-level requirements. Before choosing a motor or battery, engineers ask some questions. What top speed should the vehicle achieve? What is the desired acceleration time? What range must it deliver per charge? And what kind of terrain, load, and operating environment will it face? A city hatchback, for instance, will have a modest top speed around 120 kilometers per hour and limited acceleration demand. But an electric truck requires extremely high torque at low speeds. The engineering requirements transforms the performance metrics into the EV powertrain component selection. So, the first step is always to define performance targets. These targets drive the choice of the motor power rating, battery capacity, gear ratio, and even cooling system. This approach takes real-world needs like top speed, acceleration, climbing ability, and driving range, and turns them into actual torque, power, and energy numbers. That way, we can see that a small city car, a long-distance bus, and a high-performance SUV all need very different components, even before we start looking through the parts catalog. Let us begin with the battery pack, which is the heart of the EV. Battery selection depends on capacity, voltage, chemistry, discharge rate, temperature capability, and lifespan. Engineers first determine how much energy the vehicle consumes per kilometer. A small EV may use 100 watt-hour per kilometer, whereas a larger SUV may use 180 to 220 watt-hour per kilometer. Multiplying this by desired range gives us the required battery capacity. The next decision is battery chemistry. Lithium-ion NMC is preferred for high energy density. LFP is used when safety and long cycle life are priorities. Solid state is emerging, especially for premium applications. Voltage level also matters. A higher voltage architecture, like 400 volts or 800 volts, reduces current, improving efficiency and reducing cable thickness. Porsche Taycan uses an 800 volt system for fast charging and high performance. Engineers also consider thermal management, liquid cooling versus air cooling, packaging form factor, pouch, prismatic, cylindrical, battery placement for weight distribution, safety and crash protection. Thus, selecting a battery pack is a multi-dimensional decision involving performance, safety, and cost. We compare the common 400 volt EV system with the newer 800 volt setups. Moving to 800 volts means lower current, thinner cables, and much faster charging, and it often uses silicon carbide electronics. But it also adds cost because insulation and components must handle higher voltage. So we learn when it makes sense to upgrade for performance, and when sticking to 400 volts keeps the vehicle affordable. Once battery requirements are established, the next major component is the electric motor. Motor selection is driven by torque, power, efficiency, RPM range, size, and cost. The first step is calculating the torque needed to achieve target acceleration and gradability. Gradability means the vehicle's ability to climb slopes. For example, an electric scooter needs 25 to 30 Newton meter at the wheel. A passenger car may require 150 to 250 Newton meter. An electric bus may need thousands of Newton meter delivered through gear reduction. Motor topology is also important. Permanent magnet synchronous motors, PMSM, offer high efficiency and compact size, ideal for passenger cars. Induction motors are cheaper and robust, used in early Tesla models. Switched reluctance motors are simpler but can create noise and vibration. Peak power and continuous power ratings must be selected carefully. Peak power handles short bursts like overtaking, while continuous power determines cruising ability. Motor cooling. Air or liquid cooled also affects these ratings. Weight and packaging constraints influence motor diameter and length. The placement, front axle, rear axle, or in-wheel, affects motor geometry as well. We compare three motor types and what they're good for. PMSMs are compact and efficient, but use magnets. Induction motors avoid magnets and are tougher, but a bit less efficient. Switched reluctance motors are cheap and can run very fast, but they make more noise and need careful control. Each option changes cost, controller complexity, materials, and power capability, so we pick the motor that matches the vehicle's needs and budget. Power electronics act as the brain and nerves of the EV powertrain. The inverter converts the DC battery power into AC for the motor. Selecting an inverter requires matching its current rating, voltage rating, switching frequency, and cooling ability to the motor. Higher switching frequency offers smoother control but increases heat. Engineers choose switching devices such as silicon IGBTs or silicon carbide MOSFETs based on efficiency and cost. Silicon carbide is becoming popular in high voltage EVs because it reduces switching losses and allows faster charging. The DC-DC converter, onboard charger, and power distribution modules must be selected to ensure safe energy management across the vehicle. Finally, software integration is key. Motor control algorithms, field-oriented control, torque control, and fault diagnostics must match the chosen motor and inverter. We match the inverter's RMS and peak current ratings to what the motor actually needs. Then we decide whether to use IGBTs for lower cost or SiC devices for high frequency, high voltage efficiency. Finally, we balance switching losses, heat dissipation, heatsink size, and the life of the DC link capacitor, so the system delivers strong performance without sacrificing reliability. We look at the trade-off in switching frequency. Higher kilo Hertz gives smoother torque and better driving feel, but lower kilo Hertz cuts switching losses and heat. The final choice depends on the power device, the motor's inductance, and how much cooling the system can handle. All three factors help us pick a PWM frequency that meets noise, vibration, harshness, and efficiency targets. Unlike IC engines, EVs do not require multi-speed transmissions because motors provide high torque at low speed. However, EVs do need a fixed reduction gear to reduce motor RPM and increase wheel torque. Selecting the gear ratio is extremely important. If the ratio is too high, the vehicle accelerates well but loses top speed. If it's too low, top speed increases but acceleration becomes sluggish. Gear choice also affects noise because high-speed motors can create gear whine. Engineers choose between spur gears, helical gears, or planetary gear sets depending on noise, packaging, efficiency, and cost. High-performance EVs, like Porsche Taycan, use a two-speed gearbox to balance acceleration and highway efficiency, but most EVs stick to a single-speed reduction system. Differential selection also depends on whether the vehicle is FWD, RWD, or AWD. In dual-motor EVs, software replaces mechanical differentials, enabling torque vectoring. Thermal management is central to powertrain selection. Batteries, motors, and inverters must stay within safe temperature ranges to avoid degradation or power loss. Engineers choose between air cooling, simple but limited, liquid cooling, common in EVs, refrigerant-based cooling used in high-performance vehicles. The cooling system must manage both heat generation during acceleration and cold performance during winter. Cooling circuits also influence packaging layout, pump sizing, and energy consumption. Improper cooling can reduce battery life, motor power, and charging performance, so this becomes one of the most important selection decisions. We compare air cooling, liquid cooling, and even refrigerant cooling for batteries, motors, and inverters. We look at the actual heat each component produces, plus hot climates and fast charging goals. Those factors decide how much pump power we need, how big the radiator should be, and what coolant chemistry to use. The goal is simple: avoid temperature derating and protect the components for a long life. Let us highlight how everything in an EV powertrain is connected. Battery voltage affects which inverter devices you can use. The motor's kV rating decides the gear ratio. Cooling limits determine how much continuous power you can deliver. So you can't choose components in isolation. Mechanical, electrical, and thermal factors must be balanced together to create a cost-effective system. We underline that every component choice affects cost, weight, and safety. Engineers are constantly trading between them. For example, spending more on silicon carbide electronics might let you use a smaller battery, or choosing heavier LFP cells might improve fire safety. The final design must satisfy both the finance team and the regulatory approvals, so it's all about finding a balanced, acceptable spec. Let's finish with a simple rule. First, decide what you want the vehicle to do, then choose the right battery size. Pick a motor that matches it, select an inverter that can handle the power, set the correct gear ratio, and make sure the system stays cool. If we follow this step-by-step method, we get good range, high efficiency, and happy customers. Without this discipline, an EV program will fail. Let's end with one key message. No single part makes an EV great. A good powertrain comes from balancing many skills, running simulations, and checking results on real hardware. With that approach, we are ready for the next step, moving from ideas to numbers and turning theory into real case studies. Thank you all for your attention. To summarize, selecting EV powertrain components is a careful engineering process that begins with performance targets and ends with meticulous matching of batteries, motors, inverters, gear reduction systems, drive lines, and cooling systems. Every decision affects range, efficiency, cost, weight, safety, and customer experience. This is why powertrain selection is considered a multidisciplinary process involving mechanical, electrical, thermal, and software engineering. Thank you, and in the next session, we will study the EV powertrain dynamics, which would help us towards EV component sizing.